Welcome to the deep dive. Today, we're really getting into the nuts and bolts of handling data efficiently. We're looking at some key chapters from Jeremy Kubica's book, Data Structures the Fun Way.
Yeah, it's a great one. He doesn't just give you dry theory. He uses these really clever analogies. Coffee comes up a lot, actually, which I appreciate.
Me too. And it really helps explain how just organizing your data differently can totally change how fast your code runs.
Exactly. It's all about that impact on algorithm efficiency.
So we'll be covering the basics, variables, arrays, then moving up to things like trees, hash tables, even graphs. And it's all presented with pseudocode, so it's not tied to one specific programming language.
Which is great for understanding the core concepts.
Right. Our mission here is to pull out those key ideas. Why do these structures matter? How do they connect to, well, even finding the best coffee, apparently? Okay, let's jump in. Chapter 1, Variables and Arrays, the absolute basics.
Okay, so a variable, fundamentally, it's just a name we give to a location in the computer's memory. It holds one piece of data. Simple enough, right? Like a labeled box.
A single box. And then arrays scale that up.
Exactly. Think of an array as a whole row of those boxes, side by side in memory. Contiguous. All the boxes are the same size, holding the same type of data, and you could instantly get to any box if you know its position, its index.
Kubica uses the analogy of high school lockers, or like a strip mall with connected storefronts. That direct access is the key benefit, isn't it?
Absolutely. Because they're all together in memory, the computer can calculate exactly where, say, the fifth element is with just one quick calculation. Super fast access if you know the index.
But that contiguous structure has downsides too. Like those storefronts, what if you want to squeeze a new coffee shop in the middle?
Ah, yes. That's the catch. If you insert or delete something from the middle of an array, you often have to shift everything after it. Shuffle them down to fill a gap or shuffle them up to make space.
And that shifting can get really slow, especially with lots of data.
It really can. It becomes a major bottleneck.
Kubica illustrates this with insertion sort. I think he uses sorting coffee beans by freshness or origin.
Yeah, something like that. You pick one bean, then take the next, and insert it into the right sorted spot among the ones you've already placed, which might mean shifting several beans already in place.
Fine for a handful, but if you have like thousands of beans.
Exactly. The number of shifts can explode. It becomes really inefficient, what we call quadratic cost. Doesn't scale well at all.
And even just comparing things stored in arrays can be tricky, like strings.
Right. Comparing two strings means comparing them character by character until you find a difference or reach the end. That's definitely more work for the computer than just comparing two numbers. So yeah, how the data is laid out in the array impacts algorithm cost.
Okay, so arrays. Great for quick access by index, not so great if you're constantly changing the size or inserting in the middle. Now, if the data is sorted in an array, how do we find things quickly? Chapter 2, Binary Search.
This is where having sorted data really pays off. Binary search is like the classic example of leveraging order for speed. The data has to be sorted first, though.
Yeah.
That's crucial.
It's like looking for, I don't know, Colombian coffee beans in your pantry. If it's organized alphabetically, you don't start checking the T's, right?
Exactly. You immediately narrow down where it could be.
Yeah.
Binary search does the same. It keeps track of a lower and an upper boundary for where your target item might be.
And then it checks the middle.
Yep. Look at the element right in the middle of your current search range. Is it your target? Great, you found it. Is it smaller than your target?
Then the target must be in the upper half if it exists at all.
Right. So you discard the entire lower half and make the middle element your new lower bound. If the middle element is larger than your target, you do the opposite. Discard the upper half.
And you just keep repeating that, having the search space each time.
Precisely. This halving is what makes it so incredibly fast. Logarithmic time. It's how search engines can sift through, billions of things almost instantly. It's a game changer for big data sets.
Wow. Okay. And it can also tell you if something isn't there.
Yeah. Eventually, if the item isn't present, your upper and lower bounds will cross over. Like the lower bound will become higher than the upper bound. That's the signal. Nope, not here.
What I found really neat was how Kubica shows this isn't just for finding items in an array. You can adapt it.
Oh, yeah, definitely. You can use the same principle for searching within a continuous range. His example is finding the perfect amount of coffee grounds for your brew. Maybe you know the sweet spot is between, say, 15 and 20 grams.
So you try 17.5 grams.
Right. Taste it. Too weak. Okay, now you know the ideal is between 17.5 and 20. Try the midpoint of that range. You keep narrowing the range based on the outcome, just like with array indices, but you're using actual values.
That's really clever. Okay, so binary search is super powerful for sorted, static data. But what about when the data itself needs to change size all the time? That fixed size array becomes a problem again. This leads us into chapter 3, linked lists.
Yeah, that fixed size is the big issue with arrays when data is dynamic. If you run out of space, you usually have to create a whole new, bigger array and copy everything over. That's expensive.
So linked lists offer a different way, not one big block of memory.
Exactly. A linked list is made up of individual items called nodes. Each node contains two main things, the actual data value and a pointer.
And the pointer is just like an arrow to the next node?
Pretty much, it's the memory address of the next node in the sequence. So you have this chain. Node points to node points to node. It's this pointer idea that gives them flexibility.
Because you don't need them all sitting together in memory. You can just link them up from wherever they're allocated.
Precisely. And that makes adding or removing nodes much easier. To insert a node, you just need to adjust the pointers of the node before it and the new node itself.
So you find the spot, make the previous node point to your new node, and make the new node point to whatever the previous node used to point to. No big shifting operation.
Exactly. Same for deletion. You just update the pointer of the node before the one you're removing, making it point to the node after the one you're removing,
Got it.
bypassing it.
Much more efficient for insertions and deletions then, like someone easily leaving or joining a line of people.
Good analogy, but there's always a trade-off, right?
Ah, accessing a specific element, like the 50th person in line.
Yeah, that's where linked lists are slower than arrays. With an array, you jump straight to index 50. With a linked list, you have to start at the very beginning, the head node, and follow the pointers one by one.
Traverse the chain.
Right. You follow the lengths, first node, second, third, all the way to the 50th. That sequential access takes time. So something like binary search doesn't really work well on a standard linked list because you can't instantly jump to the middle.
But for situations where you're adding and removing things a lot, like maybe managing tasks waiting to be processed, that flexibility might be worth the slower access.
Often, yes. It depends on the application's needs. And Kubica also points out you can use pointers within arrays or linked lists too. Like, instead of storing a huge chunk of data directly in an array slot or list node, you store a pointer to that data. Useful if the data itself varies a lot in size, like different length strings or complex records.
Ah, so the array or list just holds pointers, and the actual data lives elsewhere. That makes sense for managing varied data.
It's a very common and powerful technique. Indirection, they call it.
Okay, storing, finding. Now let's look at structures defined by how you use them, how you add and remove things. Chapter 4, stacks and queues.
Right. Stacks and queues are more about defining a specific behavior or protocol for accessing data. A stack follows the last in, first out rule, LIFO.
Like a stack of papers on your desk. The last one you put on top is the first one you take off.
Exactly. The main operations are push, which adds an item to the top.
And pop, which takes the top item off.
Yep. And you can implement a stack pretty easily using an array.
How does that work? You just keep track of the top.
Yeah, you have an index variable, often called top, that points to the position where the next item should be pushed.
Yeah.
Push. Put the item at the top index, then increment top, pop, decrement top, then retrieve the item at the new top index. Since you're only ever adding or removing at one end, you avoid all that costly shifting we talked about with array insertions deletions in the middle.
Clever. Okay, so that's IFO. What about queues?
Queues are first in, first out, FIFO.
Like the line at the coffee shop, first person in line gets served first.
The perfect analogy. The operations are on queue, which adds an item to the back or rear of the queue.
And dequeue, which removes the item from the front or head.
Right. Essential for managing things in order, like print jobs or customer requests.
Now, implementing a queue with an array, doesn't that create a potential issue? As you dequeue items from the front, you leave empty space, right?
It can, yeah. If you just keep adding to the back and removing from the front, your queue data kind of drifts through the array, leaving wasted space behind it.
So what are the solutions?
Well, one way is to shift all the remaining elements forward every time you dequeue. But again, shifting is slow.
Right. Back to that problem.
A better way is often to treat the array like it's circular, a circular buffer. When the real pointer reaches the end of the array, it wraps around to the beginning if there's empty space there left by dequeues. Requires careful management of the head and tail pointers, though.
Or you could just use a linked list for a queue, couldn't you? Seems natural.
Absolutely. Linked lists are often a very natural fit for queues. Adding to the tail and removing from the head are very efficient operations.
Okay, so stacks and queues manage order based on entry-exit rules. What if we need a structure that's dynamic, keeps things sorted, and lets us search efficiently? Chapter 5, Binary Search Trees.
Right, so we saw binary search is fast on sorted arrays, but arrays are bad for insertions deletions. Linked lists are good for insertions deletions, but bad for searching. Binary search trees, or BSTs, try to give us the best of both worlds.
How do they manage that? It's a tree structure, right?
Yep, it's hierarchical. You have nodes, and each node holds a value. Crucially, each node can point to up to two child nodes, a left child and a right child.
Like a family tree, but only 2 kids max per parent.
Sort of, yeah. Nodes with children are internal nodes, and nodes with no children are leaf nodes, the end of a branch.
And the key is how the values are arranged in this tree.
That's the magic. It's called the binary search tree property. For any node in the tree, everything in its left subtree, all nodes reachable via the left child pointer, must have a value less than the node's own value. And everything in its right subtree must have a value greater than the node's value.
Ah, so there's an inherent order baked into the structure itself. Kubica had that funny analogy about a PR department organized by humor levels.
Yeah. Less funny people report to the left, funnier people to the right. It maintains that order. And this property is what makes searching efficient.
How does the search work then?
You start at the top, the root node. Compare your target value to the root's value. If your target is smaller, you know you only need to look in the left subtree, so you follow the left child pointer. If your target is larger, you follow the right child pointer. You repeat this at each node, always choosing just one path down the tree.
So you're effectively doing a binary search, but on the tree structure, discarding half the possibilities at each step.
Pretty much, yeah. On average, if the tree is reasonably balanced, this gives you that fast logarithmic search time again. But unlike the sorted array, adding and removing nodes is also typically efficient, usually logarithmic on average.
How do insertions work?
You basically search for the value you want to insert. When you reach a point where the next step would be to follow a null pointer, meaning the value isn't there, you insert the new node right there, maintaining the BST property.
And deletion
Sure.
seems trickier.
It can be. Deleting a leaf node is easy. Deleting a node with one child is also fairly simple. You just bypass it. Deleting a node with two children is the complex case.
Yeah.
You usually need to find either the largest value in its left subtree or the smallest value in its right subtree, move that value into the node you're deleting, and then delete the node where you took the replacement value from, which will be an easier case.
Okay, sounds a bit involved. And you mentioned if the tree is reasonably balanced, what happens if it's not?
The worst case scenario. If you insert items in, say, strictly increasing order.
Like A, B, C, D.
Exactly. Each new node just becomes the right child of the previous one. You end up with a structure that looks just like a linked list, all skewed to one side. In that case, searching degenerates back to linear time, just like scanning a list. You lose the logarithmic advantage.
Kubica's example was that coffee log with timestamps, right? If they're always increasing, the BST becomes unbalanced.
Yep. That's why more advanced self-balancing trees exist, like AVL trees or red-black trees. They automatically perform rotations during insertions and deletions to keep the tree balanced. More complex to implement, but they guarantee logarithmic performance.
So, BSTs, great combination of search and dynamic updates on average, but watch out for balance. Now, what about searching specifically for strings? BSTs work, but comparing strings can be slow. Enter Chapter 6, Tries.
Right. Tries, spelled T-R-I-E, often pronounced try to distinguish from tree, are specifically optimized for string operations. The problem with strings in a standard BST is that comparison. If you have coffee in CoffeeScript, you compare C-O-F-F-E-E before finding a difference. That's wasted effort if you have lots of shared prefixes.
So how do tries avoid that?
Instead of comparing whole strings at nodes, a try branches based on individual characters. Each level down the try corresponds to a character position in the string. A node might have children representing A, B, C, etc. for the next character.
Like Kubica's conference registration table example. First branch by the first letter of the last name, then the second letter, and so on.
Exactly. It's multi-way branching based on the character sequence. So to search for cat, you start at the root, follow the C branch, then the A branch from there, then the T branch.
And how do you know if you've actually found a valid word, not just a prefix? Like if car is in the try, how do you know ka isn't meant to be a word itself?
Good point. Nodes in a try often have a special flag or marker. If that flag is set, it means the path from the root to this node represents a complete, valid string stored in the trie. Internal nodes along the path might not have the flag set.
Got it. And the search efficiency comes from?
The number of steps to find a string is proportional only to the length of the string you're looking for. It doesn't matter if there are 100 strings or a million strings in the trie. Searching for cat takes roughly 3 steps, plus maybe some checks at each node.
Wow, that's independent of the total dataset size.
Yep. That's the huge advantage over BSTs for string searches, where search time usually depends logarithmically on the number of strings.
Insertion and deletion must follow the same character path logic.
Pretty much. Insertion follows the path, adding new nodes if a branch for a character doesn't exist yet, and sets the marker flag at the end. Deletion finds the node, unsets the flag, and might prune branches backward if they become empty and don't lead to other valid words.
So tries might use more memory, potentially, lots of child pointers per node, but they become way more efficient than BSTs when you have tons of strings, especially with common prefixes.
Exactly. The comparison cost at each step is minimal, and the search depth is limited by string length, not dataset size.
Okay, fascinating. Let's switch gears. What if we don't just want to find things, but we need to repeatedly find the most important thing? Chapter 7. Priority queues and heaps.
Right. A priority queue is an abstract concept. It's a collection where you can insert items, and you can always efficiently retrieve the item with the highest priority. Think of an ER triage system, or maybe of a bug tracker, where you always want to address the most critical bug first.
It's dynamic, right? You can add new tasks or bugs anytime, and their priorities might mix things up.
Exactly. You can intermix insertions and retrievals of the max priority item. Kubica mentions you could implement this with, say, an unsorted list. Easy insertion, slow retrieval, have to scan everything.
Right.
Or a sorted list, slow insertion, have to find the right spot, fast retrieval, it's at one end.
But neither is ideal. So heaps are the specialized structure.
Yes. A heap is typically a tree-based structure, specifically designed for priority queues. It satisfies the heap property. For a max heap, the value in any parent node is always greater than or equal to the values in its children.
So the biggest value automatically bubbles up to the top.
Precisely. The highest priority item is always right there at the root of the tree, ready to be retrieved.
And the clever part is implementing this tree using just an array.
Yeah, that's very efficient. You can map the tree structure onto an array, such that you can calculate the array index of a node's parent and children just based on the node's own index. No pointers needed.
How do you maintain the heap property when you add or remove things?
When you add insert an item, you usually stick it at the end of the array, conceptually the next available spot in the tree. Then you bubble it up. Compare it with its parent. If it has higher priority, swap them. Repeat this comparison and swapping up the tree until it's in the right place or reaches the root.
And removal, you take the root, right?
Yep, remove the root, highest priority. Then, to fill the hole, you take the last element from the array, put it at the root. But now the heap property is likely broken at the top, so you bubbled it down. Compare the new root with its children. Swap it with the larger of its children if they have higher priority. Repeat this down the tree until it settles into place.
Okay, sounds efficient. And there are min heaps too.
Yeah, same idea, but the parent is always less than or equal to the children. So the minimum priority item is always at the root. Useful for finding the smallest element quickly.
And you can even update priorities of items already in the heap.
Yes, though it might require bubbling the updated item up or down to restore the heap property. Essential for things like task schedulers where priorities change.
Cool. Okay, mostly 1D data so far. What about multiple dimensions, like finding nearby coffee shops on a map? Chapter 8, grids.
Right, the nearest neighbor search problem in multiple dimensions. Checking every single coffee shop against your location. That's a linear scan way too slow for large data sets.
Yeah, imagine checking 100,000 shops and just sorting by, say, latitude doesn't help find the closest one overall, as Kubica points out.
Exactly. So grids offer a spatial partitioning approach. You overlay a grid onto your 2D or higher D space, divide it into bins or cells. Then, for each data point, each coffee shop, you figure out which grid cell it falls into.
So instead of searching all shops, you first find your grid cell.
Yep. And then you start by looking only at the shops within that same cell, much smaller number to check. Of course, multiple shops might be in the same cell, so you often use a linked list or something similar within each cell to hold its points.
But what if the closest shop is just across the boundary in the next cell over?
The edge case. You can't only check your own cell. A common strategy is, first, find the closest point within your cell. Let's say it's 100 meters away. Now, you only need to check neighboring cells that are potentially closer than 100 meters. If a neighboring cell's boundary is already 200 meters away, you don't need to look inside it.
So you check your cell, then expand outwards to nearby cells, but only if they could possibly contain something closer than your current best find.
Exactly. Pruning the search space. It's like Kubica's analogy of finding the closest person at a party. You check immediate neighbors, then look a bit further, maybe across the fence into the next group if necessary.
Got it. A big improvement over checking everyone. Now, can we make this partitioning more adaptive? Chapter 9. Spatial trees, quad trees, KCED trees.
Yes. Grids have fixed cell sizes. Spatial trees like quad trees offer hierarchical adaptive partitioning. A quad tree is for 2D space. It starts with a whole area. If it contains too many points or meets some other criteria, it divides itself into 4 equal quadrants.
Northeast, northwest, southeast, southwest.
Yep. And then each of those quadrants can also be recursively subdivided if needed. So areas with lots of data points get divided into smaller and smaller quadrants, giving you finer resolution where it matters.
Like zooming in on a map in a dense city area, as Kubica described it.
Exactly. Searching involves starting at the root and figuring out which quadrant your target point falls into, then descending into that quadrant subtree, repeating until you find the point or the region it should be in.
And KZ trees, they generalize this.
Right. KD trees work for K dimensions. Instead of always splitting into 4 in 2D, a KD tree splits the space along one dimension at a time. At the root level, it might split all the points based on their x-coordinate, via example, using the median x value. At the next level down, it might split based on the a-coordinate, then maybe x again, cycling through the dimensions.
So the regions aren't necessarily squares or cubes, but hyperrectangles.
Exactly. They can be more flexible in shape than quad-tree regions. Each node stores the dimension it splits on and the splitting value. Searching involves comparing your target point's coordinate for the node's splitting dimension to decide whether to go left or right.
Kubica mentions building them in bulk versus adding points dynamically.
Yeah, building from all points at once, bulk loading, can often result in a more balanced tree than adding points one by one. But both approaches work. Insertion, deletion, and search follow similar recursive logic, using the splitting dimension at each node to guide the traversal.
So quad trees and KD trees offer more sophisticated ways to index spatial data than simple grids. Okay, let's shift back to pure speed for lookups. Chapter 10. Hash tables. Hyper-optimized lookups.
You got it. Hash tables are all about speed for insertion and especially lookup, almost instant on average. The core idea is using a mathematical function, the hash function, to directly calculate where an item should be stored in an array.
Like Kubica's coffee pantry analogy, you instantly know where the Sumatra is. You don't have to search shelf by shelf.
Exactly. The hash function takes the key, like Sumatra, and converts it into an array index, a bin number. You go straight to that bin.
What if two different keys happen to calculate the same index? That's a collision, right?
It is. Collisions are unavoidable in practice unless your table is huge and sparsely populated. So you need a strategy to handle them. It's a classic trade-off, except the possibility of collisions, which might slow down lookup slightly in those cases, in exchange for incredibly fast average performance.
And a common way to handle them is separate chaining.
Yep. Instead of storing the item directly in the array bin, each bin holds a pointer to a linked list. If multiple items hash to the same bin, they just get added to that bin's linked list.
So, to look something up, hash the key to get the bin index, go to that bin, then potentially scan through a short linked list.
That's the process. Hash dat dash dash. Go to bin traverse list if needed. If the hash function is good and distributes keys evenly, those linked lists stay very short on average.
What makes a hash function good?
2 key things. It needs to be deterministic, same key always gives the same hash value, and it should spread keys out uniformly across all the available bins. You don't want clumps where lots of keys hash to the same few bins, leading to long lists. Kubica mentions Horner's method for hashing strings as a way to get good distribution.
Makes sense. So hash tables offer amazing average speed for lookups and insertions, making them super useful.
Absolute fundamental in countless systems.
Now, related to speed, what about making access to frequently used data faster, especially if the main storage is slow? Chapter 11, caches.
Caching is all about exploiting locality of reference. The idea that if you access some data, you're likely to access it again soon. Temporal locality, or access data nearby, spatial locality. So you store a copy of frequently or recently accessed data in a smaller, much faster memory area, the cache.
Like the barista keeping the most popular coffee blends right next to the machine instead of in the back room.
Perfect analogy. When you need data, you check the fast cache first. If it's there, a cache hit access is super quick. If it's not there, a cache miss, you have to go fetch it from the slower main storage, which takes longer, but then you usually store copy in the cache for next time.
But caches are small. What happens when the cache is full and you need to bring in new data? You have to kick something out, right?
Exactly. You need an eviction policy. Kubica focuses on LRU, least recently used.
Kick out the data item that hasn't been touched in the longest time.
Right. The assumption is that if you haven't used it in a while, you're less likely to need it again soon compared to stuff you just used.
And how do you implement LRU efficiently? You need to know what's in the cache and the access order.
Typically, use a combination of two structures. One, a hash table. This lets you instantly look up if an item is in the cache and find its location. Two, a doubly linked list. This list keeps track of the access order. Every time an item is accessed, a hit or a miss that gets loaded, you move its corresponding node in the list to the very front, most recently used. The least recently used item will always be at the tail of the list.
Ah, so the hash table gives fast lookup, and the linked list maintains the usage order. When you need to evict, you just grab the node at the tail of the list and remove it from both the list and the hash table.
Precisely. It's a very common and effective pattern.
Kubica also mentions other strategies briefly, MRU and LFU.
Yeah. Most recently used, evict the newest, sometimes useful if you access things sequentially just once, and least frequently used, evict the item accessed fewest times, needs counters. LRU is very common, though. Caches are all about that speed versus memory trade-off.
Okay. Now, what if the entire data set is just too massive to fit in main memory? We need to deal with slow disk access. Chapter 12, B trees.
Right. When your data lives primarily on disk, like in a large database, the bottleneck isn't usually CPU time. It's the time taken to read data from the disk, which is orders of magnitude slower than accessing RAM. B trees are tree structures specifically designed to minimize the number of disk reads required to find data.
How do they do that? By making the tree shorter and wider.
Exactly. Unlike binary trees where each node has at most two children, nodes in a B tree can hold multiple keys, in sorted order within the node, and have multiple child pointers. Kubica's analogy is those collectible card binders. Each binder node holds many cards, keys, and tabs point to other binders, child nodes.
So when you read one node binder from disk, you get a whole bunch of keys to check at once.
Yes. You load a node from disk, do a search, like binary search, within that node's keys to figure out which child pointer to follow next. Since each node covers a wider range of keys and points to many children, the height of the tree is much smaller than a binary tree for the same amount of data. Fewer levels means fewer disk accesses to get to the data you need.
And they handle insertions and deletions while staying balanced.
They do. Insertion involves finding the right leaf node. If adding the key makes the node overflow, too many keys, the node is split into two and the middle key gets promoted up to the parent node. Deletion is more complex, potentially involving merging nodes that become underfull or borrowing keys from siblings to maintain the minimum key requirement per node. But the structure ensures balance and logarithmic access time in terms of disk reads.
Crucial for databases and file systems, then.
Absolutely fundamental.
Okay, let's switch to something completely different. Probabilistic structures. Chapter 13, Bloom filters. These sound intriguing.
They are. A Bloom filter is a very space-efficient way to test if an element is possibly in a set. The key thing is, it can give you false positives, saying something might be in the set when it isn't, but it never gives false negatives. If it says something isn't in the set, it's definitely not there.
How does it achieve that with minimal space?
It uses a bit array, an array of zeros and ones, and several different independent hash functions. When you add an element to the set, you hash it using each of the hash functions. Each hash gives you an index into the bit array, and you set the bit at each of those indices to 1.
Okay, so one element might flip multiple bits to 1.
Right. Now, to check if an element is in the set, you hash it with the same set of hash functions again. You look at all the corresponding bit positions in the array. If any of those bits are still 0, you know for sure the element was never added because adding it would have set that bit to 1. No false negatives.
But if all the bits are 1,
it might be in the set. Or it's possible that those bits were set to 1 by the insertion of other elements that happen to hash to some of the same indices. That's your potential false positive.
I see. So it's like a quick, maybe definitely not check. Kubica's analogy was the event organizer who might mistakenly think someone's there based on a vague description.
Exactly. Super useful as a pre-filter. Check the Bloom filter first. If it says definitely not, you're done. If it says maybe, then you do the more expensive check, like querying a database. Saves a lot of unnecessary expensive checks.
Very clever use of probability and hashing. And speaking of probability, Chapter 14, skip lists. Another probabilistic take on speeding up searches.
Yeah, skip lists aim to get performance similar to balanced trees, like logarithmic search time on average, but potentially with simpler insertion-deletion logic. It starts with a basic sorted linked list.
Which we know is slow to search.
Right, so a skip list adds multiple levels of forward pointers to this list. Some nodes, chosen randomly, get an extra pointer that skips over the next node and points to the one after that, level 2. Some of those nodes, again chosen randomly, get another pointer that skips even further ahead, level 3, and so on.
So you have these express lanes running alongside the main linked list.
Kind of. Higher levels have fewer nodes, but the pointers jump much further. Kubica uses analogies like squirrels jumping between tree branches at different heights or passing messages between tall buildings.
How does searching work with these levels?
You start at the highest level pointer from a special head node. You follow that level's pointers as far forward as you can without going past your target value. Then you drop down to the next lower level and repeat the process, follow its pointers as far as possible without overshooting. You keep dropping levels until you're at the bottom level, the original linked list, where you do a final short scan to find your element or confirm it's not there.
So the upper levels let you make big jumps to get close quickly, then the lower levels refine the search.
Exactly. The randomness comes in when you insert a new node. You randomly determine how many levels of pointers the new node will have, usually with decreasing probability for higher levels. Then you stitch it into all those levels.
And this randomization gives good average performance.
Yes, on average, it provides logarithmic time complexity for search, insertion, and deletion, much like balanced trees. But the algorithms can be arguably a bit simpler to implement than, say, red-black tree rotations.
Interesting. A probabilistic alternative to balanced trees. Finally, Chapter 15, graphs, where the structure comes from the data itself.
Precisely. In all the previous structures, we were kind of imposing a structure, array, list, tree, hash table, onto the data to help us access it. With graphs, the relationships between the data items are the structure.
Nodes representing things, edges representing connections between them.
Yep. Nodes or vertices are the entities. Edges are the connections. Edges can be directed. A points to B, but not necessarily B to A.
Right.
Or undirected. A and B are connected. Edges can also have weights or costs associated with them, like distance between cities or cost of a connection.
And the power comes from algorithms that use this graph structure.
Absolutely. The structure isn't just for storage, it's essential for the algorithms. Kubica highlights a few key ones. Dijkstra's algorithm finds the shortest path, lowest total weight, from a starting node to all other nodes in a weighted graph. Think mapping apps.
Okay, what else?
Prim's algorithm finds a minimum spanning tree, MST, in a weighted, undirected graph. That's a way to connect all the nodes together using a subset of edges with the minimum possible total weight. Useful for network design, like laying cables.
And the third one?
Kahn's algorithm for topological sort. This applies to directed acyclic graphs, graphs, with directed edges and no cycles. Gives you a linear ordering of the nodes such that if there's an edge from A to B, A always comes before B in the ordering.
Like figuring out the right order to do things based on dependencies. Kubica's coffee brewing steps analogy.
Exactly. You can't add milk before you brew the coffee. Topological sort figures out a valid sequence. Graphs are just everywhere in computer science, modeling everything from social networks to program dependencies to chemical reactions.
Wow. Okay, so that's a whirlwind tour through a lot of data structures. Let's try to wrap up with the big picture from the postscript.
Yeah, the core theme that keeps coming back is how the choice of data structure dramatically affects algorithm performance. Just sorting data enables binary search, turning a slow linear scan into a lightning-fast logarithmic one. That's huge.
And there are always those trade-offs, aren't there? Space versus time, simplicity versus efficiency.
Always. Arrays are simple, fast indexed access, but inflexible size. Linked lists are flexible, great for inserts deletes, but slower sequential access. Hash tables are super fast on average, but have collision handling overhead in worst-case scenarios.
Kubica also mentions amortization. Sometimes a costly setup operation pays off over time.
Right, like sorting an array once allows many fast binary searches later, the initial cost is amortized over the subsequent benefits.
And we saw how complex structures are often built from simpler ones. Tries evolving from trees, linked lists used inside hash tables or grid bins.
It's all about understanding the building blocks and how to combine them. Understand the why behind each structure, its motivation, how it's built, where it shines, and its limitations. That's key to choosing the right tool for the job.
So, to sum up, data structures aren't just academic concepts, they're fundamental tools. Choosing the right one depends heavily on your specific problem, your data's characteristics, and what you need to do with that data.
Definitely. And maybe a provocative thought to leave listeners with. Think about the apps and websites you use every day. Search engines, social media, recommendation systems, they all rely heavily on data structures working behind the scenes. What structures do you think they might be using? What trade-offs might the engineers have made? What kind of coffee optimization is happening under the hood to give you that experience?
That's a great question to ponder. If you want to explore these ideas further, definitely check out Jeremy Kubica's Data Structures the Fun Way. You can find more info at nostarch.com. Think about how these concepts might apply to challenges you face. Thanks for joining us on this deep dive.